The last idea we're going to look at with integration is using symmetry. So if we know it's an odd function or an even function, that can help us out. Things like that. So first of all, even function. Remember, that's the one where function negative x is equal to function x. It's reflected in the y-axis. So you can go, instead of going from minus a to a, because you've got the symmetry, you could go 2 times 0 to a. Now on that, if you were to shift the whole curve over, and you notice that the function had symmetry, say, in the line x equals, 2. So instead of being symmetric about the y-axis, but then it was symmetric around 2, then you could still use the same idea. So, well, I just called it c for a constant. So if you'd shifted the whole thing, and the symmetry now is at x equals c, and you're going from c minus a to c plus a, then you could say it's 2 times c to c plus a. It's still the same idea, you've just shifted the problem along the x-axis a bit. It's a pretty rare occasion you'd use it, but you never know if you spot it. Similarly with the odd function, you'll remember odd functions, they're the ones with rotational symmetry. Function negative x is negative function x, and what we saw when it was rotated around the origin, and that symmetry would be equal 0, because the bit below would cancel with the bit above. But again, if you had a whole horizontal shift, so if you now notice, hang on, I can rotate this around c, and the bit below is equal to the bit above, well then that's going to be 0 as well. So it's still the same idea. Now the third one's quite interesting. It's this little, again, it's to do with shifting the curve, but if you want to integrate from 0 to a function x, you actually get the same value as when you integrate from 0 to a of function a minus x. Let's prove it. So there's 0 to a of function a minus x. So how I'll prove it is I'll go, well, hey, let's substitute u for a minus x. So du is minus dx, and playing with the limits, we'll get, well, x equals 0, u is a, and vice versa. When I substitute in then, I get minus the integral from a to 0 of function u to u, but the negative sign means I can swap those limits round. And so I have 0 to a of function u to u. Well, if it's a definite integral, it doesn't matter what the pronumeral is, because we're going to substitute in anyway. So I can make it 0 to a function x dx. Again, it's a rare occasion, but if you notice that, the limit's going from 0 to a, and actually it might be easier to go a minus x. And I suppose one of the classic examples might be trig. If you're going from 0 to pi on 2, because then you can substitute in pi on 2 minus x and get the complementary ratio. So that's one spot where it sometimes comes in handy. Keep in mind, odd function times odd function gives you even, odd times even's odd, even times even's even. So basically the same type of function multiplied together gives you even, different types of function gives you odd. If you ever forget, bring it back to the simplest one. Use y equals x as your odd function, x squared as your even function. And so odd times odd would go x times x, oh that's x squared, even. Odd times even, x times x squared, oh that gives me x cubed, odd. Even times even, x squared times x squared, oh that's x to the 4, even. So if you ever forget, just bring it down to a real simple case. Okay, so let's have a look at this one. Sine cubed x. Now, you can waste a lot of time with this type of question now, because we've looked at all sorts of techniques for tricky integrals. We could use our technique for sine cubed. But here, if we recognise what we got is an odd function, and we're going from -1 to 1. Let's see, and an odd function cubed is odd, so we know it is an odd function, so answer 0. Bang, got it. Which is going to be a heck of a lot quicker than doing the actual integration and so on. So if you do spot symmetry, it can obviously save you a fair bit of time with a question like that. Here's one of the ones where the 0 to a idea works out quite nicely. Because x squared times root 1 minus x, I can't expand out into two terms because of the square root sign. But I notice under the square root sign, we've got 1 minus x, and I'm going from 0 to 1. So I can change that. Everywhere I see an x, I'll replace it with 1 minus x. So the x squared becomes 1 minus x all squared, but the square root of 1 minus x is just square root of x. That I can now expand out into single terms, which can be integrated. and we get, there it is, x to the half minus 2x to the 3 on 2 plus x to the 5 on 2, add 1 to the power over the power, substitute in, and we get an answer. So, as I say, it's an unusual case, but it works because of those limits, the 0 to 1, and oh look, I've got 1 minus x in there, so I can take advantage of that. Now what about improper integrals? We haven't really said a lot about improper integrals. So there's how we define it. It's a definite integral where the integrand is undefined at some point. So limits is what we have to use to work out whether or not a solution would exist. The classic is our hyperbola. If I wanted to integrate that from 0 to 1, well 1's not an issue, but 0 obviously is, because it's undefined at 0. So what we really do is we say, well 0 is what's causing me the problem. So I want to find the limit as n approaches 0 from n to 1 of dx on x, and see whether this gives me a definite answer. Sometimes it will, sometimes it won't. Well, we know that's log x when we integrate. So we're saying it's minus log n, the limit as n approaches 0 of minus log n. So now we think about log curve, and what happens as n approaches 0? Well, it's still undefined. So this one's no good. No. So the actual integral is undefined. We wouldn't be able to work that one out. However, this one, x e to the minus x squared, and we're going to go from 1 all the way to infinity. So we've now got a problem at the end point on the right hand side. So I'll change it and say, well, what I'm really investigating is the limit as n approaches infinity of 1 to n of x e to the minus x squared. Now this is a nice one, I don't have to do it by parts, because x of course is part of the derivative of minus x squared. So we can just go minus a half e to the minus x squared. Substitute in n, substitute in 1. So now think of your curve e to the minus n squared. Now e to the minus n squared, as we go into infinity, that actually approaches 0. So we can get a value here. It'll just be, well the first term will be 0, but I'll have minus a half times minus e to the negative 1. So 1 on 2e. So even though the area you would think would be infinite, because it's going on forever and ever, it actually has a definite value to it. So we could work that integral out. So that's what's called an improper integral. A little bit about using areas and inequalities. Now, if I imagine you're looking at the picture and you've got 3 curves, and gx is below fx, which is below hx, all the way between a and b. Then the area under those curves must also go in that order as well. Okay? So the integral from a to b would be less than or equal to the integral, well, a to b, they're all a to b. The integral of gx would be less than or equal to the integral. Because if you draw those curves, I'm assuming these curves, of course, are above the x-axis. I guess that's the other bit. But the area underneath it would get bigger and bigger as we go up. So let's look at an HSC question that was quite interesting. So n is going to be a positive integer greater than 1. We're going to look at the area of the region under the curve of our hyperbola from x equals n minus 1 to x equals n. Now, what they told us is that area clearly is going to be between the area of those 2 rectangles, what we sometimes call the inner rectangle and the outer rectangle. The actual area would be trapped in between 2. Show this particular inequality is what they're asking us. Okay. Let's say inner rectangle, that area will be less than the actual area under the curve, which will be less than the area of the outer rectangle. So 1 times 1 on n, that would be the inner rectangle, is less than the integral, that would be the exact area, is less than 1 times 1 on n minus 1. Okay, so 1 on n, the integral is log x, it's less than 1 on n minus 1. Substitute in the n and the n minus 1. Now, what we're trying to prove didn't involve log, it involved exponentials. So what did I do from here? Well, I've multiplied everything by n, basically. So it becomes 1 is less than n log n on n minus 1. is less than n on n minus 1. Then in the middle I can use my log law, bring the power in. And now I'm going to exponentialize all three terms. Because if you think of your exponential curve, if the values that I'm substituting in are increasing, and that's what I'm going to substitute into e to the x, then the answer is 2. If you've got your exponential curves, what you sub in is getting bigger, then the answer must be getting bigger as well. Because we know our exponential curve is continually increasing, would be the technical term there. So e to the power of 1 would be less than e to the power of log, well, e to the power of log cancels, is less than e to the power of n on n minus 1. We're getting close to what they wanted. I'm now going to turn it all upside down, but if we turn them upside down, we've got to change the inequality signs. So you notice they've all gone to greater than, but it looks horrible like that, so I'll rewrite it so they're all less than, and in fact we have the answer. The n minus 1 on n I've rewritten, but it is 1 minus 1 on n. The 1 on e, well that is e to the negative 1. And the 1 on e to the n on n minus 1 is, there is a negative sign in front of that vinculum there. I don't know if you can spot it, but it is actually a negative n on n minus 1 there. So that's using this idea of trapping the areas to prove an inequality. We'll see more of that when we look at inequalities in more detail later this year. Okay. So we now have the last couple of exercises in Patel. We have Cambridge. Notice in Cambridge, that a minus x idea, they used 2a minus x instead of a minus x. It's just a constant. I guess they do 2 because of symmetry, so they doubled it for some reason. And then of course, the 100, which is a tradition that goes back a very long way.